Muy bien, pues vamos a dar inicio a esta sesión del coloquio. Y pues es un verdadero placer para mí presentar a un entrañable amigo del Departamento de Matemáticas. Y creo que la ocasión voy a permitirme tomar un par de minutos nada más para hacer una breve recolección de lo que representa esta amistad entre nuestro ponente y el Departamento de Matemáticas del Cinvestav. Pues, sobre todo aprovechando que hay mucha gente joven en el auditorio, y muchos de nosotros pues no estuvimos en aquellos entonces y vamos a tener ahora la oportunidad de conocer, entiendo, algunas de las historias relevantes. Pero, bueno, pues nuestro departamento se fundó a principios de la década de los 60, si recuerdo bien, en el 61. Y fue fundado por dos de las personas más importantes, las figuras matemáticas más importantes en México y a nivel mundial, los profesores Samuel Hitler y José Aden, que en menos de 10 años, en poco menos pasando la primera década, habían hecho una actividad sobresaliente, habían hecho actividad académica, sus ideas, su investigación había sentado en los derroteros de las futuras direcciones de la topología algebraica a nivel mundial. Y justamente en aquella época, un recién egresado de su doctorado, entonces, realizó múltiples visitas a nuestro departamento en la década de los 60s y 70s particularmente. Pues no estábamos aquí, bueno, yo ya había nacido para entonces, pero pues no estaba por aquí, y pues nuestro ponente fue colaborador, sentando muchas de estas ideas, colaborando en uno de los problemas centrales más calientes, más hot de entonces, era el problema de encontrar el mínimo espacio euclidiano en donde una variedad dada pudiera ser representada dentro de. Pues hay dos versiones, versión encaje, versión inversiones, etcétera. En particular, cuando la variedad uno identifica puntos antipodales de esferas, surgen ideas interesantes y se puede caracterizar en términos algebraicos. Quizás nuestro ponente nos estará platicando un poquito. Estas ideas con las que nos va a platicar ahora tienen relevancia en ese contexto. Este problema ya no es tan, bueno, no está resuelto en general, ni siquiera para espacios proyectivos, pero ha desarrollado mucho de las técnicas de la topología algebraica actual en el mundo. Así que sin más miramientos, déjenme introducir a nuestro ponente del día de hoy, el doctor Kee Lam, Emeritus Professor from the University of British Columbia, and he will be telling us about the new constructions for non-singular bilinear maps. Please.
Well, nice to see many familiar faces. I remember all these faces. I may not remember all the first names, but the last names are still in my mind. Jesus mentioned that I was a frequent visitor to the Cinvestav, starting from the early days and ongoing. Well, actually, the reason that I was visiting so frequently is not 100% because the peso has wood buying power. The first time I came, I was supposed to visit for a summer month and then go back to the United States to take up some teaching job. But then the United States was nasty in those days as it is now. How nasty? it did not give me the visa to go back. Yeah. I went to the embassy in Reformer and said, who are you? No, you cannot go back. No visa. So I was stuck. And fortunately, Jose Adam and Sam Hitler suggested that maybe they can extend my invitation to stay longer. And therefore, I had to stay longer. I had nowhere to go. And only by taking advantage of that longest period of stay, I applied to a Canadian university. I got a teaching job for the next term. So that's why I kind of remain in contact with Mexico more often, perhaps, than many other visitors. That is the reason. And the lesson of all this is that even if the US does bad things all the time, some of those bad things can turn out to be quite good. So this is how it is. Okay, as I put down in my abstract, the bilinear map, you can call it F, takes a pair of vectors, one R-dimensional and one S-dimensional, and associated another vector that's n-dimensional. And this n-dimensional vector has to be linear in x if y is fixed, and linear in y if x is fixed. That's what bilinear means. So any such map is a bilinear map, and for notational convenience, I will even suggest that just write this f of y as x cross y. So if you have a bilinear map, that means that you have a way to take two vectors, one R-dimensional and one S-dimensional, and through this map, multiply them together to result in an n-dimensional vector. All right. This is, well, we are all familiar with such so-called vector products. Two vectors, possibly of different dimensions, maybe of same dimension, multiply in some way through the formula for this map, and resulting in an n-dimensional vector. So this is kind of a very simple mathematical object, which can be studied by algebra, by topology, and even by some other numerical means. Okay, so this is a bilinear map, and I mentioned two examples in the abstract. Take two three-dimensional vectors and take the cross product, you result in a three-dimensional vector. The cross product that we teach all the time to our undergraduates. Cross product, example 2. So here you take the x vector and the y vector and you use some kind of product to multiply them. This time I would introduce the tensor product. So that tensor product x tensor y becomes a 9-dimensional vector, dimension multiplied. And this R9 is all this R3 tensor. What's the difference between these two kinds of products? Most remarkably, this one has 0 divisors. X can be non-zero, y can be non-zero, but the cross product can be 0. This one has no 0 divisors. X is non-zero, y is non-zero, the tensor product will be non-zero. In this case, when 0 divisors are there, we say that the bilinear map is singular. And if there are no 0 divisors, any two non-zero vectors multiply into non-zero, then we say that the bilinear map is non-singular. So there are two kinds. For example, let's mention one more. Well, of course, this is also very familiar. This is the dot product of two ordinary three-dimensional vectors. This one is singular. Two dot products. The dot product of two vectors can be zero without each of them being zero. So there are two kinds, and the more interesting ones are the non-singular kind. All right, non-singular kind. All right, here then is a mathematics problem. So far unsolved. It's an open problem, what I'm going to say, and it's a problem that is very deserving of further research work. And I believe it's also a problem that is suitable for undergraduate or graduate thesis. The problem is find all possible non-singular bilinear maps and classify them. Find all the ones that you can think of. For example, here this one is a type 339. Here's one. And the multiplication of complex numbers. It's just the usual product of complex numbers. This one is non-singular for the good reason, because the norm of the product of the two complex numbers is equal to the product of their individual norms. All right. So similarly, then you have quaternions. This is type 444, because the quaternion is a four-dimensional vector over the reals. All right, so 444. And later on, yes, these are so-called octonions. They are all type 88. I don't have time to go over the detailed history of these things, but I suppose everybody at least have heard of them. Euler first did this one and studied it, introduced complex numbers into mathematics, e to the I theta, and then after, I believe, more than 100 years, Hamilton found this, and after Hamilton, about 5 to 6 more years, Cayley found this. And that was only the beginning. Then it got stuck. Because obviously, if the trend goes on, one is going to expect the 16 from 8 dimension now double to 16 dimension of this type. So for many years, people try to get from here to there. Nobody succeeded. And that is beginning to be interesting. This kind of thing they call division algebras, because you are multiplying two things without zero divisors, so that you can get the inverse of each non-zero element, and therefore they fulfill the axioms of a division algebra. Not necessarily commutative, but it is a division algebra. If there were a division algebra whose elements are 16-dimensional vectors, and two of them multiply into a third 16-dimensional vector, that would be very nice, right? Then one goes on to 32 and so on. All right. However, there's no such thing. There's no such thing. And it took some time to prove. And this then is the first phase of the development of the subject of non-singular bilinear maps. And it then, of course, now elected the question I just quoted: find and classify all possible non-singular bilinear maps. You classify according to some scheme. Let me not specify what scheme. You have a good way to classify them. Maybe geometrically and so on. Maybe just let me mention that there are two types, right? For one type in the classification, the absence of zero divisor is due to a norm property. That is one type. The norm property means that you take the norm of the product, and if that turns out to be always equal to the product of these two norms as real numbers, then this is the norm property. Of course, if you get the norm property, you assume that it's non-singular. So that's one type of examples. We don't even know all examples of this kind nowadays up to this moment. And the other kind is not to have such a norm product, but still you have no zero divisors. Everybody can think of a general example. Multiply two vectors of various dimensions. The result is non-zero when the two factors are non-zero, but we don't have this norm product. Well, that is obvious. So this one has the norm property. And the next one I would call polynomial. Multiply two polynomials in the usual way you know, and then you get the product that has no zero divisors. If your polynomial has coefficients from a field or a division algebra. All right. So this one again is non-singular, but it fails to have the norm property. At least now I give a very rough classification now, the ones with norm property and the ones without norm property. Each has its own interest. And they turn out to be interesting in surprising ways. For example, this norm property, maps of this type, enable people in differential geometry to construct harmonic maps between rigid spheres. And maps of this type, non-singular, but maybe without the norm property, still enable the topologies and the geometers to do immersion theory of one manifold into another. So each type is interesting. And that is up to the 1920s or so, that is the scheme. I'll go on with the history in a little while, but let me just look at the problem from another different angle. Just hopefully I can convince at least a part of the audience here that to study this kind of bilinear maps is interesting, non-singular or singular. And the classification also is interesting. So let us look at this thing in material science. Here, imagine you have an alloy made up of two kinds of metallic materials in layers, alternative layers, one lying next to each other like this, all right? Now, you see this alloy there. I'm going to explain why there are some bilinear maps involved in this picture. Okay, so let's see how this material condition can lead to very naturally into bilinear science. Let us analyze the interface at the point in the interface of the two materials and see what happened. All right, so I hope my diagram is not too small. Now, I'm only taking a point in the interface between the red and the black, and the green one, the green sigma is the interface. I'm at a point in the interface. This point is away from the origin, so the position vector from the origin to this point is denoted by vector x, a three-dimensional vector. And now I want to analyze the mechanics of these two materials interfacing and maybe pushing each other by some kind of a friction force or strain or stress tensor and so on. So let's analyze the mechanics of this. Take one point in the interface and take a vector coming out from it. Then the following mechanical thing will happen. So here is, and all things that are happening will be indicated in green. So I have a point x away from the origin with a position vector, and at this point I have specified a vector which I'll call v. Okay, now this x is on the interface, so it is subject to two forces. All these materials, we say that they are stressed materials, just like a loaded bridge stressed by the presence of many cars and so on. Okay, so this red material has a so-called a stress tensor, which will do something to this point. In fact, it will do something to imaginary, take a little surface element, a tiny piece of surface, as they always do in differential geometry. Take a piece of surface element and then analyze what happened to it. All right. Now, the stress force from the red side is going to try to push this little piece of surface away. You specify where you are, you specify this little piece, namely you specify it to be perpendicular to this vector. So there would be a red force. There would be a red force here trying to push it away due to the presence of the red material. Similarly, it is the black stuff also will push that little piece in some other way. So there is I don't have a black now, so I'll do it yellow. So the black material exercise also some stress or some strain or some tension on the same little piece, and pulls it away in a different direction. All right. Now, mechanically, what should happen? Mechanically, what should happen? Here is this guy being pushed away by two different forces, one from either side. And what should happen? All right. In usual stable situations, the two layers would be like that. It won't slide, right? If it slides, it's unstable. So in a stable alloy, rigid one, perhaps well-constructed one, you won't have sliding, all right? So now try to express the sliding or the absence of sliding by using the red vector and the yellow vector. Well, they need not be the same vector, they need not be opposite either. However, there are components on that tangent plane. So I take a little bit of plane, I call it tau. Tau is perpendicular to the vector v. It will be a tangent vector of that interface surface. I'm sorry, it would be the where is it? This one. It will be the tau would be the tangent plane of this interface two-dimensional surface. That little piece of plane element should not slide. In other words, those two vectors in two colors will project to this plane and project to opposite components, equal but opposite components, so that the two sliding forces balance on each other. Red tries to slide it this way, yellow tries to slide it that way, and they don't slide, so that means that these two sliding forces pass out. So here then is a linear algebra situation. I start with the position vector x, which is in R3. I start with the vector v, which signifies what one would like direction I'm considering. So I have this x and v here. All right. And I'm going to balance out, writing down the effect of sliding. So this one, what will you do? First, the stress tensor will push it. Let's see, the red one would have a stress tensor will get that piece of surface determined by x and v, and then the yellow ones will also get a force on x and v, subtract the two of them, and project it to the tangent plane tau. Project that difference to the tangent plane tau. Also like that, after projection. No sliding means it projects to zero. So this one and this one eventually will go to this tau. Tau is a two-dimensional vector space, so it is a R2. Okay. So here is a bilinear map because the stress tensor is supposed to be linear, right? Linear elasticity. So R3 plus R3 all the way through this process to R2. what's the adjective I should use to describe this map for balancing? Well, what happened? I got a non-zero x because there really is a real point. I got a non-zero vector v. It really specifies a direction for me. So x is not zero, v is not zero. But when I come here, no sliding. That means I get zero. Okay. I get zero there. So this pair go there. And if I use this notation, here is a zero divisor. X non-zero, v non-zero, but their vector product defined in this sense has to be zero. So the singularity of a non-singular bilinear map is therefore a built-in feature, in fact, perhaps the most important feature in studying elasticity. All right. So let us use that as an example to convince ourselves, maybe some of ourselves, that looking into this difference is interesting. Of course, the interest doesn't quite lie in there, because if we connect up this kind of idea with practical problems, practical things happen in 3 dimensions, right? Or at most 3 dimensions, tensor 3 dimensions. Dimension cannot get very high. However, one can ask the general problem of absence of zero divisors in very high dimensions. So the beginning of the mathematics is in concrete applications, but immediately one generalizes to higher dimensions. Okay, so now that I hope will sufficiently motivate the problem, and this diagram that is an explanation of this thing. After the 16, 16, 16 have been ruled out, people try to do the second best. And so the next name historically would be Hurwitz and Verhoeven and Radon. And that takes us to the turn of the 19th century into the 20th century. Well, they find non-singular bilinear maps of the following types. Let me write down a few. I will not spend time on explaining this pattern, but you can figure it out. There's a periodicity of going on. Every 4 times the things repeat itself. So they found these ones, and these ones are also without zero divisors, and they are without zero divisors because of the norm property. So that's good. And you can imagine now, when Hurwitz found this, and knowing that this one is not possible, and it certainly creates a question in everybody's mind. 9, 16, 16 is not possible according to Hurwitz. 16, 16, 16 is not possible according to according to Hurwitz also, in fact, by analysis of linear algebra or finite group representation. Let me not go into details like this, but you can see that there's a question mark. For example, can I get 11, 16, 16 to be non-singular? And for quite some time, nobody knows. Nobody knows. And so that is one way for mathematical activity concerning these things. The next phase of activity came with they begin to see that knowing these maps that they exists, that they can be quite easily constructed. They saw that a lot of geometric applications are possible by using these maps. All right. For example, Hawk used this case. Used it very well in algebraic geometry, and eventually that led to the Hawk blowout. It basically based on this. Hamilton himself used this to make the study of physics in rigid motions of rigid body into a very nice form using the quaternions. All right. The octonions, what was the use of octonions in the hands of geometers and differential geometers? The octonions, they go beyond the physical dimension of 4 now, and they're 8-dimensional. So the octonions also were found very instrumental and useful in what? Bringing in the G2, the exceptionally root G2. It's the group of automorphisms of octonions. All right, so these people, being very good topologists themselves, found many uses of them. One use that they found is the immersion problem of real projective spaces. So especially James. Classically, one knows that the classical projective geometry, which happens in this real projective plane, that cannot be subsumed by Euclidean geometry. All right. In the old days, 17th, 18th century, the projective geometry, which is the geometry in this universe, is not part of Euclidean geometry. In the language of these geometers, you cannot put the projective plane into 3 dimensions in the one-to-one continuous manner. All right. Otherwise, there's no need to do projective geometry. If this one is in there, then all the geometry happens here, will also happen here, then projective geometry would be subsumed by solid ordinary geometry, solid Euclidean geometry. No point. But that's not the case. We know that this is not the point. All right. And then, how about higher dimensional projective spaces? In particular, well, you work a little bit, you saw that this is not possible, and using some geometric means, that's why often Sipo and James all come in, all the way up to dimension 9. Try to put it in some Euclidean space of some dimension, so that the geometry on the 9-dimensional projective space can be subsumed by the solid geometry in that dimension Euclidean geometry. All right, this is an embedding problem. Sometimes they relax the embedding problem a little bit. They don't want the whole thing to be one-to-one continuously put in a high-dimensional Euclidean space. You just want the embedding be replaced by immersion, namely, roughly, double points can be allowed. You put these things in, but you will allow some double point, even some triple points and so on, or even a singular curve, self-intersecting curve, but not in a very bad manner. So this is an immersion problem. And how many dimensional Euclidean space would you need so as to be vast and big enough to accept the RP9 to come in to live there comfortably as a guest and to do all the geometry there? So these are the kind of problem is considered by these people. And what's the connection? The connection now, now that my talk today stops now. All right. Those are what do you call it? Before what's the word? Appetizer. It's an appetizer. Appetizer is over now. Okay. All right. But then there was a question of I give myself a 9-dimensional real projective space. I want to study him by realizing it inside some Euclidean space. How many dimensional Euclidean space do I need? By the way, today's talk, which given by me, is actually predestined almost 100 years ago. That means the things happening 100 years ago already predestined that today I come here to give a talk in the following sense. All right, if we look at all these numbers, even these numbers, these are the numbers entertained by such people, and so on, almost 100 years ago. And you notice that they are powers of 2, right? So powers of 2 in some concrete experimental way, or by simple human experience, power of 2 is very significant in this problem. Why? At first, they did not know why. All right. Hopf began to know a little bit why, by the Hopf condition, which maybe I will mention later. But they still could not explain very well why. For example, is this number going to be the power of 2? Right. That you squeeze the Alpine line, nobody knows. And why do I say that my talk today is predestined to be the talk here today? Predestined some 100 years ago. Let me tell you what happened yesterday. Dr. Ishikida, when I picked me up from the airport, drove me here, and then went to see Estella, and that's to say the key. If there's any problem, just call me. All right. I said, what's your extension number? She gave me this. She gave me this extension number. Then he took me into the office, which was used to be the office of his father. He said, well, here's a phone. Let me get you an extension number. So we follow up. And then Estelle said, yeah, okay. We'll impose an extension number on that unit. And here it is. Let me write it down. You see, you told me anything concerning to this talk, for this extension number. All right. So that's why I say that this is destiny, the working of destiny, right? Because I almost want to cancel my flight not to come, but destiny established 100 years ago, forced me here to come. You just see the evidence of this, right? Okay, so that's an answer. Now the appetizer is over. Let us start the talk today. I hope you permit me to go in this phase and in this manner, and emphasizing a little bit of history, only letting some mathematics come in at the end. All right. Now, next bunch of people, along the trends of thinking of this problem. You all know the names. Next. After that phase of geometers coming in, and this is the main force now. Start in about 1964. Of course, all these people study Hopf very well, study Tico very well, study James very well, and we want to continue the research. All right. So in 1964, Sinrod had a sabbatical leave from Princeton University, and he decided to visit his two earlier very bright students, Adam and Taylor. So they invited Sinrod to come to join them in the building over there, the old building on the other side. Or maybe not, maybe the first time the building was just to be built, but they invited Sinrod to come down to spend a part of his sabbatical leave together with them. And the three of them keep on talking. Many things they talk about, but there's one thing that I know that they talk about. Sam and Jose asked Sinrod a question. They asked him a question. They told Sinrod, Norman, if you can get me a non-singular bilinear map of type, different from all those old guys, but useful for us modern people of this type. So Sam and Jose said that demand CMOD to provide them an example of a non-singular bilinear map of this type. In other words, to find a bilinear map from our hand on our hand. R16. And CMOD, then what for? What do you use it for? And Sam and Jose said, well, if only you could give me an example like that, I will be able to put this RP9 into 13-dimensional space. And that will be optimal. That's what they told CMOD. They did not know whether that's possible. They depend on CMOD to get the answer of the existence or non-existence of this kind of bilinear map which has no zero divisors. CMOD spent somewhere there, could not get the answer. All right. But something was going on in his mind. All right. Well, CMOD thought to himself that, well, after my sabbatical leave, I'm going back to Princeton and resume teaching my graduate courses. I'll do algebraic topology, of course. And just before I had my sabbatical from Princeton, I know that Princeton put in two new graduate students. They seem to be interested in topology. CMOD said to himself, when I go back, I'm going to mention this problem by Sam Hitler and Jose Adam to those two guys, all right? And I'll try to interest them to think about it. I'm too busy, I won't think about it. So those two guys just entered Princeton and now they are in their first or second year, right? All right, so I guess you should know the names of those two guys. CMOD said that, well, one guy comes from Hong Kong, such a Pai and Vision from Hong Kong. Another guy also entering around the same year or just 1 year apart. Another guy came from Mexico. All right. So CMOD said that I'm going to pull these two guys to work on this very specific problem. Okay. Oh, there's one guy's name that I don't need to mention. You all understand. All right. But the other guy is, yeah, one guy is, there's another guy. What's his name? From Lam. He did not take up this problem. The open book. The open book.
Petrovsky.
The non-working. The open book. Winkelkamper, yeah. So CMOD said, oh, Winkelkamper and so from Hong Kong will be at Princeton, and I'm going to tell them to think on this problem. All right. So after he returned to Princeton, he brought us, Winkelkamper and myself, and maybe one or two other people that I don't remember, into his office and said, look here, find or disprove the existence of such a non-single bilinear map of type 10, 10, 16. This opens up the whole period. This opens up the whole period. All right. So, eventually, in my PhD thesis, I found it to be there. All right, I found, and I still remember CMOD smile when I went into his office and showed him a piece of paper. It is also a piece of paper like this with little square boxes in it. I showed him some matrices that will imply the existence of this. And then I at that point I decided that part of his square should go on to support my summer work. But so this brings things into the modern era. Find and classify all possible non-singular bilinear maps and exhaust their types, explain them, study their geometry, and explain also that why other kinds of maps are no longer possible. The other map must be singular. This is still an open problem, and as I emphasized once more, it's still worth thinking about. All right, now let me check my time. How do you do the finding? How do you do the classification? All right. write down some arbitrary things. Yes. Most likely they will be singular. Most likely the third dimension would be too high, so high to be of no interest to anybody. And so you have to do reasonable ones, like this 16 is less than the sum of this 10 and this 10. So it's still a very interesting ways that you can give the answer of yes or no. But how do you know? How do you know? Let me take the approach today of trying to reconstruct history and go back to the old guys, Euler, Hamilton, and Cayley, and so on, and see how they found theirs. How Euler found the 222, the compact numbers, Hamilton the 444, and right afterwards Cayley the 888, and then who was Radon and so on. Let's go back and try to understand, examine their psychology. In particular, there's one thing most interesting, I think even interesting to psychologists up to now, is that why did Hamilton take 10 years? He wanted to get the 444. Why did he take 10 years? The answer is his mind was stuck on the 333. All right. He wanted to take, well, they did normal vector product of 3 dimension and 3 dimension into 3 dimension is singular. It has 0 divisors. He wants to get a field or division algebra on R3. All right. That is doomed to fail, of course. Nowadays, we know very well that that's doomed to fail for good topological reasons. But Hamilton did not know. In fact, he may not have gone that way. He may not have thought about topology at all. He kept on pushing with 3-dimensional vectors, changing signs, giving new bilinear forms, changing the coefficient of some terms in the bilinear form, and so on. He never succeeded. It took 10 years. To the extent that, according to history recording, his son was very impatient. Okay, so we go back. Let's just take this approach of trying to go back. Let's start with Euler. How did Euler find the complex numbers? What do you think it is? Well, everybody wants to know how Euler found the complex numbers. He said that -1 has no square root. So I'm the king, I'm the genius. I invent this symbol to stand for the square root, and I just keep on playing as if this symbol is like an algebraic symbol. So therefore, we found the complex numbers. This is what we were usually told by the historians of mathematics. But let us think in his own time, in his own days, what could have happened in Euler's mind? I call it the path not given. Let's do a little bit of speculation. The path not taken by Euler. To arrive at this multiplication of so-called complex numbers, visualized as a pair of 2 real numbers or 2-dimensional vectors. Of course, in those days, they always wanted non-singular property. They hate 0 divisors. If you have 0 divisors, your algebraic system is no good. So that certainly should be in Euler's mind. I have not done many historical literature research, but I thought that maybe one path not taken by Euler is the following. He tries to multiply 2 vectors of dimension 2 in some vector product way and get a new vector, and in such a way that 0 divisors or 0 divisors more. Now, he could not have noticed that there is one such. There is one such. Even Euler is Euler. How could he have? There is a type 223 bilinear map. All bilinearity are over the real numbers, by the way. Throughout today's talk, everything is real numbers. Zeros are a 0, the real 0 to an equation and so on. This one, surely is the multiplication of two linear polynomials into a quadratic. That there's no zero divisors. All right. Only that the dimension here is slightly too high. If this had been true, well, the complex number would be discovered. All right, because you can prove quite easily by a little bit of algebra that if you get a two type, no matter what your formulas are, they will eventually be more or less equivalent to a multiplication of complex numbers, simple algebra, matrix, and so on. So it's just that little bit, a little bit too hard. The form that goes like this. So here is one linear polynomial. Multiply into quadratic. So he put a note about this. I believe it's quite likely. And okay. As long as there are ways to get this number down to 2 into a top. Euler probably did not go this far, but as present day mathematician, I guess if we are going to take up the problem again, starting from the early days, unavoidably we would have thought about this direction, right? I myself thought about this direction some time ago. I forget where. Okay. So why did Euler not insist on this? Why did he just pick up this funny guy there? Oh, nowhere. But this is very concrete. You start with something very concrete, you try to improve a little bit, then you're done. In fact, of course, this when I'll tell you how to do it in a moment, this would be an alternate way to find the complex numbers. What is the alternate way? The alternate way is that I adopt the viewpoint of polynomial multiplication. I think of polynomial multiplication as one possible type of bilinear maps, which of course they are. And I don't want zero divisors. Polynomial multiplications have no zero divisors, except that they multiply into a degree that's the final degree is too high. What if I can suppress the degree back down to 2? Is it possible? Oh, yes. Is it possible? What I mean is the following. If that's possible, then I would have drawn an alternate path and repeat what Euler did. Well, this is always, I will always keep out here, keep many identical copies of our document, and then lots of this. Now, I am going to suggest that we think this way. I take this polynomial multiplication. This is the word that appears in my abstract. Now, if you are a student of Hobbes and Seymour and so on, you know the idea of homotopy or deformation. Homotopy or deformation. Why don't I take this very concrete polynomial multiplication into a quadratic and try to set some new multiplications, deform it, until I deform it to the terminal one. So deform continuous manner as time goes on, until I find deformation such that in the final version, this is f, this is f at the end, this is f in the beginning. Suppose I manage to deform this polynomial multiplication. After I get into the new stage, I won't call it a polynomial multiplication, but I've deformed it into some other bilinear map. and I try to deform in such a way that I keep the non-singular property. In other words, I'm doing a homotopy of my solid arrow on the top through a continuous family of arrows, which are bilinear maps, which do not lose the non-singular property. Okay, I can do that, at least I can try. I can try. And this is the alternative way I think. I hope against hope that at the end, when I get to the end of my deformation, get to the end of this one turns out to be the factorization. If I manage to deform it in such a way that the final product is this map, which happens to factor through the R2, then this is what Euler would do. This is what Euler would get to. But I would be getting it different from introducing such a fellow. So I don't have to introduce anything new, nothing imaginary, everything is very concrete. I just deform in a concrete way. Is a deformation possible? Notice that you don't just deform. You can change the bilinear forms coefficient just by a tiny bit. That's a deformation. But you deform through a continuous family of non-singular bilinear maps. Yeah, that's the difficulty. Can this be done? If it is done, I would have rediscovered Euler in my own way. Yes, it can be done. It can be done. Why is it possible to do this? Why is it possible to do this? There's a reason. The reason is algebraic, but it also will yield the subsequent geometry that allows me to do the deformation. What is the reason? I'm starting from the beginning, multiply two linear polynomials into a quadratic polynomial. What basic fact that is going to help me? The basic fact is that this map is not onto. There are three-dimensional vectors there, which are not the product of those two vectors on the left-hand side. Well, when I say that it's not onto, nobody probably know what I mean. But when I say it in another way, everybody will know anyway. To say that this multiplication of two linear polynomials into a quadratic is not onto, simply says that there are quadratic polynomials with real coefficients which are not factorizable. If there's a polynomial visualized as a three-dimensional vector, it's not factorizable as a polynomial into two linear vectors. That means I cannot find two guys here on linear, non-zero linear vectors that multiply. There is such a line. There is such a line. All right. Namely, the quadratic polynomial 1 plus x squared, or 1 plus x squared times any constant, any real constant. So this map, this non-singular bilinear map, failing to be onto, is actually the key or the alternative path to Euler's discovery. All right, why? Why is it that having this irreducible polynomial is tantamount to what Euler so historically importantly did? Because this guy that fails to factorize as a quadratic polynomial is like this part of my umbrella, all right? Like there's a vector here in our field. In our field, there's this vector. I left this vector or a non-zero real multiple of it, still unfactorizable. I'll let it to be represented by this step, all right? So the things from the polynomials from the left-hand side keep on multiplying and get some quadratic polynomials. So here is the our field, all the quadratic polynomials. One on this, one on this, one on this, and so on. And they all receive pairs of points from the left-hand side. All right. But apart from the zero vector along this step, there's nobody from the left side will hit this step because it's irreducible. no two linear factors, you multiply into this 1 plus x squared times a non-zero constant. All right, now, can you do the deformation? But I'll show you the deformation. Take the points that receive image from the left-hand side, and they are maybe like those points on this surface of umbrella. You just deform until this umbrella, this part is flat. That means it becomes R2. All right. So the points which originally come on this side end up here, but it's deformed and pushed out until it's pushed into the surface of this umbrella, which is R2. So this R2 is my umbrella surface. I open it up until it's flat. Well, you can be less concrete and describe this in mathematical terms through orthogonal projections. But I think this is good enough. This is very simple, but it takes the mind of homotopy theories that is a little bit straight. You do homotopy and you do deformations. All right. So eventually, after I deform all this into that plus that, I'll forget that. That is a 2 to 2. All right. I've gotten what Euler did in some other way. If I won't repeat now. If you think along this way of thinking and try to re-examine what Hamilton did, you find that he was more or less in the same situation. He tried to multiply two quaternions into a third quaternion. All right. He would not have done that. A quaternion is a vector of 4 dimensions, so that is a cubic real polynomial. He is trying to multiply two real cubic polynomials into another polynomial, but then he has to go to dimension 6, cubic times cubic. Dimension 6 polynomial means R7, including the constant term. All right. So Hamilton was, if he had taken this path, he would have gotten an R4 times R4. And then we will have to do some modification, just like with these umbrellas, but in higher dimensional geometry. And then eventually that to this R4 times R4, cross R4 into R4. That can be done if you care to figure out go home. I will repeat it now. Right. So here is an alternate path. Then one you have to be careful. All right. Don't think that this will always give you better examples. You start with polynomial multiplication, guaranteed to be non-singular. You deform over your umbrella, and then you lower the dimension, and then you get a better example of more strong non-singular bilinear map. One has to analyze this very simple idea and very simple procedure further. For example, let us multiply two quadratic polynomials into a quatic. All right, two quadratic polynomials with real coefficients multiply into a real polynomial of degree 4. All right. In terms of bilinear maps, this would be quadratic polynomials over the reals would be R3, including the constant term. Another one, multiply into a polynomial of degree 4, including the constant term, that would be R5. So this is another polynomial multiplication, guaranteed to be non-singular. You know, this is exactly what Hamilton was struggling for his 10 years. Possibly, a possible explanation of Hamilton's struggle was that he wanted to multiply a 3-dimensional vector, another 3-dimensional vector, into a 3-dimensional vector. But the quadratic multiplication only gets him into R5, a 4th degree polynomial. So he would like to do something similar to the umbrella, according to the reconstruction of history. All right. This idea to deform this map through a continuous family of non-singular bilinear maps. But this time he's out of the coast. He's deformed this into a lot of alpha, or remain alpha. At this point, but then at the end of the deformation, we find this full image going into our field, And he would have gotten his 3D. He would have terminated his 10 years of agony and got that. But we know it's not possible. Why is it not possible? No matter how we try, he could try for another 30 years. Still not possible from this deformation approach. Very different from Euler's case. Why is it not possible? Because the situation is different. What's the difference? In the Euler case, I found a quadratic polynomial with real coefficients that fails to factorize. Right here, a fourth-degree polynomial with real coefficients, always factorized into the product of two quadratics. Fourth-degree polynomial with real coefficients, so its complex roots would be in conjugate pairs. Group the two conjugate pairs together, you will get two quadratic polynomials. Multiply them together, you get your original. So you can always do that because the roots to a real coefficient fourth-degree equation always come in conjugate pair. And therefore, this is went on to. No matter how you deform it, you'll be onto. Why? Can I deform it into not onto? No, not possible. I can use some simple homotopy theory to explain that. No. You deform it into here, still onto. You deform it into here, still onto. You deform it here, still onto. You cannot squeeze it into our thing. No way. That is why Hamilton was doomed to fail for 10 years. Okay, so this a little bit of reconstructions of history. It may sound superfluous, but it's not quite. So let me just conclude. My time is up, so allow me to just conclude. So I said that, why don't I follow up this idea and do some higher degree polynomials? And I'll just bring in more variations by using quaternions or even octonions as coefficients. All right. So eventually, after some attempt or trial, we decide to look at cubic polynomials with octonion coefficients. Multiply them together and see what happens. That is the point of view we took. Here it is. K stands for octonions. K4 means a cubic polynomial with octonion coefficients. So the constant and the three other terms, it will be a fourfold octonion. Take that polynomial, multiply with another one. Cubic times cubic is 60. So you end up with polynomial of degree 6 with octonion coefficients, including the constant term. That's the case here. So I just try to go the same path which I analyzed for Euler and Hamilton. After a lot of trial. So it is something like that. And then, well, since the polynomials are longer and of higher degree, it would be good to get a scheme to represent that multiplication. I decided to do it in matrix form. All right? No umbrellas anymore, too high. The high dimensional umbrellas are now replaced by this matrix. In this following sense, say the first polynomial is cubic, coefficients A0, A1, A2, 3, A3. The second next one is also cubic, B0, B1, B2, B3. I am going to multiply them. When I multiply them, the resulting polynomial has coefficients C0, C1, C2 up to C6. All right? And here they are. I get the C0, C1 up to C6 by summing up this 1, 2, 3, 4, 5, 6, 7. Constant term 1, 2, 3, 4, 5, 6, 6. All right. Now, so I use a matrix scheme to save myself the trouble of writing down all this polynomial multiplication. And here I play another trick. I do not use the normal matrix scheme for polynomial multiplication. For the normal multiplication of polynomials, which we use for ring theory of polynomial rings, whether the ring is commutative or not, we put the term aibj in the ij position, all right? And then we sum up a0 b0, a0 b1, a1 b0 plus a0 b1, and so on. But here, I'm not putting those terms. I took those terms and I twist it by a little bit. I twist that term by a little bit. I allow myself various ways of twist. One is, for example, a1 b0, I can change it to b0 bar a1. The bar means a conjugate, and so on. Sometimes I even put a twist by putting a minus sign in front. These terms should have been a1 b3. I twist it to minus b3 a1 bar. Then, of course, will give me, to start, a different polynomial multiplication, because I'm following a different formula to group the coefficients together. Quite similar to the original, but with twistings and change of sign and interposition. AB becomes a BA and so on. That opens up quite a few bilinear maps. Still, even after I twist, the twisted multiplication I get would still be non-singular. I guess you would agree. Because I just go ahead. The way you prove that the ordinary multiplication is non-singular, I'll just follow your way word for word, step by step. And you have to deal with terms like, let's say, you have to deal with terms like my A1, B3. I just deal with terms like minus B3, A1 bar. If those are zero, if yours is zero or mine is zero, the conclusion that one factor must be zero, because the octonians form a division algebra. So I just copy your proof of non-singularity step by step. I have now managed to get a twisted non-singular bilinear map. Well, a bilinear map that is also non-singular according to your proof. I just sit here and non-singular. Okay. Now, why do I do the twist? If I don't do the twist, it's quite likely that I will run into the difficulty of those fourth degree ones. They factorize. They always factorize, therefore creating a singularity. If I don't twist, maybe the polynomial, the 6th degree polynomial with octonian coefficients I get, maybe it will also factorize, right? If they factorize, then my hope will fail. I have to find a reasonable and lucky way of twisting so that there's some kind of absence of factorization. I have to use a multiplication, so-called multiplication, in quotation marks, namely twisting, so as to guarantee that, what? There is a polynomial on this side which will not factorize. A irreducible polynomial, at least irreducible into one cubic times another cubic. I have to find one. Maybe the classic one won't do it, but I twist it hopefully with luck I can do it. I twist it away. And indeed, there was a way. That way was found after a lot of trial. So there's one polynomial over here that is not the product of two guys from the left-hand side. And the same thing will apply. This is the polynomial that failed to factorize. And then, so all the products of the qubits will only land up in here, and then I just do that. That will cut down the dimension from 56 at least down to 55. So this is K7. K is 8-dimensional. K7 is 56-dimensional. I'm running into high dimensions now, which is geometrically more interesting. But that's 56. 7 times 8 is now, which is whole 56, now is now down to 55. There's the normal surface to this single non-factorizable line. In this way, you get some new examples. So that corresponds to the equivalent of the title, and these are the examples. So the scheme is like this. All right, I multiply K4 into K7, deform, go to K7, which is now 56, but at the end of the deformation, I end up into 55. All right, got a new example. That helps. So that's a tiny bit on our attempt to classification. I got some conjectures here. I got to classify here. All right, I got to classify here. I got very interesting questions. For example, can this be squeezed? I don't guarantee that the way I squeeze it is the optimal thing I can do. Maybe any other I can squeeze first. Maybe, who knows? You have to deal with polynomials, with octonian coefficients, and multiplications of those, which unfortunately fail to obey the commutative law or even the associative law. And after you twist, it fails so badly to be like classical that the polynomial 1 may not serve as an identity. You twist it so much. Never mind, the non-singularity is there. You still have non-singular bilinear map. So once we get this one deformed down into here, gaining 1 dimension, then we examine it very closely. And by taking this one and finding subspaces U in this R32, V in this R32, and follow this arrow, they end up in some subspace W of this guy. All right. Then I get another new non-singular bilinear map, U cross V into W, where the U's dimension is somewhat less than 32, so did V, and the W's dimension is somewhat less than 55. And suddenly I can go quite high dimensions. All right. These are the ones that one can get from this single idea. So now, lots of things to classify. One thing to be classified is this 27 times 27 in the 49 dimensions. And another one is 18 in the 32. The next kind of question is that have I done my utmost best in this list? All these come from the paper. You say, yes, if I find this UVW, just carefully and give it time and keep on finding them. There are lots of them. A certain particular U, I will color in green. Another certain particular V, I will color in red. Will end up in W in this scheme that I introduced today, so that the U is 10-dimensional, the V is 10-dimensional, and the W is 16-dimensional. So after almost 50 years, I answer Professor Stimmel's question in another way. I get my 10, 10, 16. When I submitted my PhD thesis to him, I had no idea that this is the way. I had no idea. I just did stupid thing. But now I can manage. You don't waste all your time in your 50 years. You waste only 47 years. This you have something. So this is something I can, which I like to report to you. Thank you very much.
Are there any questions for the speaker? Pregunta.
So this twisted product of cubic octonial polynomials, it's completely ad hoc. Does it extend to higher degree polynomials?
Over the octonials, when the coefficients are octonial, it's very difficult to study polynomial.
Sure.
How do you factorize them? And of course, the left and right factorization will do, and sometimes there are conjugates involved. And I don't know a good criterion of telling about whether a polynomial with octonial coefficients can be tested for factorizability. In these lower dimensions, well, to say the truth, you just try hard. Keep on trying and try hard. So the verification takes pages and pages, but still possible. But if you go on the next one, some brave hard people. You have to take whether a 14-degree polynomial with octonial coefficients could or could not be factorized. You assume it be factorizable, you try to deduce a contradiction, then you're in hell. We have tried. We know that we have to give up, really depending on new ideas. So here is the source of new ideas. There's still many things that I don't have time to talk about. I'll be around for the next 2 or 3 days. What room? 305. So if you feel like talking more about it, by all means, all the time, I'll be in that room most of the time until Friday. Okay, thank you very much.
Here's a nice acknowledgement.
Oh, thank you, thank you, thank you. Thank you.